Welcome. This is a video presentation of the paper, A Universe from Itself, the Geometric Mean Expansion of Space and the Creation of Quanta, Part 1, The Revelation of Delta E. The first thing we're going to do is review what a geometric mean is. If we take two numbers, for example 2 and 4, and add them, we get 6. If we divide 6 by 2, the number of numbers we added, we get 3. 6 divided by 2 is 3. That's an arithmetic mean. That's the mean that most of us are familiar with. If instead we multiply the two numbers and take the square root of the product, we get the geometric mean. In this example, we'll multiply 2 times 4 and we get 8. If we take the square root of 8, we get approximately 2.8. This is the geometric mean of the two numbers. A common way of explaining the geometric mean is by the use of a right triangle. We have a right triangle here. Here's our 90-degree angle. And actually there's 3 right triangles here. We got a second one here, and this is the angle. And we have a third one here. All 3 triangles are self-similar. The height is this point here. And we find that if we take side A and multiply it by side B, the answer is the height squared. If we take the square root of the product of side A times side B, we get the height, and this is the geometric mean. We have here a right triangle, which we've drawn at a larger scale here. We have our 90-degree angle, and in the starting condition we have side A equal to side B. We're going to start the triangle moving, and we can see the 90-degree angle is maintained as the triangle moves across. In addition, note that the height, h, stays the same as the triangle moves. Our triangle shows us that side A times side B still equals the height squared. Side A has grown enormous and side B has shrunk considerably, and we can see here that B is very tiny, and as the triangle were to expand out further this way, side A would become larger and larger and side B would become smaller and smaller, still maintaining the geometric mean relationship. A square or series of rectangles might be more revealing to the nature of the geometric mean argument we're about to discuss. We have a square here. Side A, side B, both equal to 1. The product is the area, and then we're going to define that as a constant. It's not going to change. So we start distorting the rectangle here, and we see as side B gets bigger and bigger, side A gets smaller and smaller and smaller. All the while, the area, the product of side A and side B, maintains constancy. Let's look again at our square, our starting square. As we lengthen this bottom side indefinitely, this other side gets smaller and smaller and smaller. The curve is a hyperbola, and it never reaches the bottom. Looking at a series of rectangles maintaining a geometric mean relationship, we get the area, say, of this particular rectangle by multiplying this side against this side here. And this is the smallest aspect of this rectangle, and this is the largest aspect of this rectangle. To get the area, we take the smallest times the largest. This is an important consideration, as we'll see shortly. So we need to know that the area comes from the smallest times the largest, and if we're maintaining a constant product, we have a geometric mean relationship. The geometric mean relationship of the two sides of the square is such as one side goes to 2, the other side goes to a half. Double it to 4, the other side goes to 1/4. If you extended that side out to be 1,000, the other side would be 1 over 1,000. And there's no limit. 10 to the 1,000th would be 1 over 10 to the 1,000th. What we find is the small is as infinite as the large. And that's a very critical point in this geometric mean model that we're putting together. Let us look now at the revelation of delta E. In the paper, the Hubble constant is a measure of the increase in the energy of the universe. We determined that Fred Hoyle's mass estimate of the universe is the correct mass value. His estimate was the speed of light cubed, divided by 2 times the gravitational constant times the Hubble constant. Our equation for the Hubble constant is 2 times the speed of light divided by the radius of the hyperverse. We'll take our value for the Hubble constant, which is 2c divided by the radius of the hyperverse, and insert it into the Hoyle mass equation. And the result is r sub h times the speed of light squared divided by 4 times the gravitational constant. That's the mass of the observable universe in hyperverse terms. We'll take our equation for the mass of the observable universe and convert it to energy. We know that energy is mc squared, so we'll multiply this by c squared, and we get the energy of the observable universe is equal to r sub h times c to the 4th over 4g. We're going to take the derivative of the energy of the observable universe in respect to the radius of the hyperverse, and we find c to the 4th over 4g. We'll rearrange this equation here, and we find that delta E sub O is equal to c to the 4th over 4g times delta r sub h. We know that delta r sub h is equal to 2c, so delta E sub O comes to c to the 5th over 2g. Numerically, delta E sub O is a very large number. It's approximately 1.8 times 10 to the 52 joules per second. Notice that delta E sub O is equal to c to the 5th over g over 2, and that's 1/2 the Planck power. Let's now look at the time-energy uncertainty relation. This famous physics relationship says that delta E times delta T is greater than or equal to h bar over 2. This is the reduced Planck's constant. We know that delta E sub O, that's the change of energy for the observable universe, is equal to c to the 5th power over 2g. So let's ask a question. What is delta T for the observable universe? So let's do the math. We know that delta E sub O times delta T sub O is equal to h bar over 2. That's the time-energy uncertainty relation. Divide each side by delta E sub O, and we find that delta T sub O is equal to h bar divided by 2 times delta E sub O. We know that delta E sub O is equal to c to the 5th over 2g. We plug that in and we find g times h bar divided by c to the 5th. Therefore, delta T sub O is equal to g times h bar over c to the 5th. And g times h bar divided by c to the 5th is the Planck time squared. It's a very significant result. So T sub O is equal to the Planck time squared. Numerically, we find that the Planck time squared is equal approximately to 2.9 times 10 to the minus 87th seconds squared. And this is a very small number. Let's look now at delta T sub O divided by the age of the universe. Delta T sub O is the Planck time squared divided by the age of the universe. These are the equations we use to determine it. And we get this expression here. Numerically, this expression comes out to be approximately 6.6 times 10 to the minus 105th seconds. We will define this value as small time, our smallest unit of time. Delta T sub O divided by the age of the universe, our 6.6 times 10 to the minus 105th seconds, will be shown as T sub S. Small time, we've seen, can be expressed as delta T sub O divided by the age of the universe. We've seen this expression already. Small time can also be expressed as the age of the universe divided by this particular function here, r sub h divided by 2 times the Planck length quantity squared. This is our first time we've seen this in this particular video, and we're going to see a great deal coming shortly. But right now, let's focus on this. Small time being equal to h bar divided by 2 times the energy of the universe. Taking our value for small time h bar divided by 2 times the energy of the universe. We'll rearrange by multiplying each side by E sub O. And we find E sub O times small time is equal to h bar over 2. E sub O is our largest quantity of energy, and T sub S is our smallest unit of time. So we have E sub O times T sub S is equal to h bar over 2. E sub O is our largest unit of energy. T sub S is our smallest unit of time. From the time, energy, uncertainty relation, we have delta E sub O times delta T sub O is equal to h bar over 2. And this is our largest change of energy, and this is our smallest change of time, and both of them equal h bar over 2. We know that small time is equal to delta T sub O divided by the age of the universe. And we know that delta T sub O is equal to the Planck time squared. So we can say that large time times small time is equal to a constant, the Planck time squared. This is our largest unit of time and our smallest unit of time. When we multiply them, we get a constant, the Planck time squared. So we have three equations we can look at. Delta E sub O times delta T sub O is equal to h bar over 2. E sub O times small time is also equal to h bar over 2. And large time times small time is equal to the Planck time squared. All of these are constants. And in each of these cases here, we have a large value, the largest value in this category, times the smallest value in the category. So we have the largest times the smallest is equal to a constant. These three equations are all geometric mean equations, and they suggest that the universe is undergoing a geometric mean expansion. At this point, let us assume the universe is undergoing a geometric mean expansion and examine the consequences.